through a pointer, search the linked list to see if data item 7 there exists in this is there exists in the linked list or not. If like manager does not find item 7 in the linked list, then like manager knows that until now no transaction has any lock on item 7. So like manager can add item 7 to this linked list, and then as you see, under each data item there is another linked list. This linked list is related to transactions that have done like requests on this data item. For example, transaction 1, transaction 8, and transaction 2 has done requests, like requests on data item I23. So there is a linked list here in below of item 23, and in this linked list there are transactions that has like requests on this data item. As you see, for some of the transaction we have a box, we have a dashed box, and for the others we have a white box. White box means waiting request, and dashed box means granted request. So here transaction 1 and transaction 8 has granted locks on data item 23. So data item 23 is locked by transaction 1 and transaction 8, but transaction 2 is waiting because transaction 2 the request of transaction 2 is an exclusive lock on data item 23, which is not compatible with the locks of transaction 1 and transaction 8. Transaction 1 and transaction 8 has shared mode locks on data item 23, and they have granted locks. Their locks are granted. I mean that T1 and T8 has lock at the moment on data item 23, but transaction 2 is waiting because its lock request is not compatible with the previous locks that transactions have on data item 23. Also here you see data item 7, and you see a linked list below it which has only transaction 23. This means that transaction 23 has a granted lock on item 7. Or here you have item 912, and again you see transaction 23 has a granted lock on this item. For item 4, here we have a linked list under, we have a linked list below it, which has two transactions, T1 and T23. T1 has a granted lock, but T23 is waiting for a lock on item 4. So when a transaction has when a transaction sends a request, a like request on a data item, like manager first search data item in this array and finds the related index, finds the index which is related to that data item. Then search the linked list. Search the linked list, the related linked list to find data item. If it does not find data item in the linked list, then it knows that no other transaction has liked the data item, and the data item is free. But if like manager finds a data item in the linked list, then it knows that some transaction have likes on the data item. Then it checks the linked list of transaction in below of data item. For example, suppose a transaction sends a like request for data item 23. Like manager finds the index of data item 23 uh, and find this pointer. Search linked lists and find data item 23 here. So like manager knows that some transaction has like on data item 23. Then search the linked list of transaction below the data item. Here, this linked lists show that transaction T1 and T8 have granted like on data item 23, and transaction 2 is waiting. Then if another transaction tries to like 23, its request is added to the end of this linked list. This linked list is a queue. Is a queue, uh, uh, and if the new request is not compatible with the previous one, should be added to the end of the queue and should be waiting. If the new request is compatible with the previous likes, then it can be granted and should be added to the list, but it should be granted, and it does not need to be wait. If there is any question about this issue, please ask me.
Transaction have 23. If I want to search about the transaction 23, it is in the linked list.
Transaction 23, or do you mean transaction 23 or data item 23?
Data item.
Data item, okay.
Yes, doctor. Please, can you please explain more?
Uh, when, for example, suppose transaction 10, okay, uh, execute um, execute like S on data item 23, okay. Suppose transaction 10 execute operation like S on data item 23, okay. When this operation is executed, a message is sent to like manager, and then like manager knows that transaction 10 wants to like data item 23 in a shared mode, okay. Like manager first finds in this table, finds in this array the index of data item 23. Suppose the index is started from 1, 1, 2, 3, 4, 5, 6, 7, 8, and so on, okay. for example مثلا 2021 and so on. Like manager uses a hash function, okay, hash function. What is hash function? Hash function is a function, is a function as you know in mathematics and as you know in programming. Function maps an input to an output. Input is data item. Data item is mapped to index. Okay, for example, hash function item 23 will be 1. This means that integer checks the request. Okay,
Sorry, doctor.
please.
Thank you, doctor. The transaction 10 is add to the waiting because we use the queue for transaction.
because
Transaction 10
there's
is wait.
starvation.
Yes, or I
Yes,
know it's
transaction
we
10.
use now a queue for transaction for its waiting. First in, first out. So the transaction 10 is waiting, will be execution after the T2.
Transaction 10 is added to the end of the
Yes,
queue, and its state is waiting. Why it is waiting? Because there is another transaction
it's
which is
waiting.
waiting. Okay,
Now,
before transaction 10, we have a transaction 2. We have transaction 2 which is waiting. So we do not. Like manager does not grant the request of transaction 10, because if like manager grants the request of transaction 10, then transaction 2 has a starvation.
yes,
Because
doctor, but why T2 is waiting?
okay,
Why we not do
T2,
upgrade or downgrade for it?
um, yes, T2 is waiting because transaction T1 and T8 has a lock, has already a lock on item 23, and the request of T2 is not compatible with the request of T1 and T8. As you know, if you remember the compatibility table, please let me
Yes, doctor.
bring the table. Let me bring the table. We have a compatibility table. If two requests is compatible, then we can grant both of them. For example, if two transaction has a shared mode like request, like S and like S, like manager can grant both of them. But if a request is in X mode, then it is not compatible with the other request. And like manager cannot grant both requests. One of the requests should be granted, okay, and one of them should be waited. So here in the table, uh, transaction 1 and transaction 8 has compatible requests. For example, suppose T1 and T8 has uh, like S shared mode, like, okay, both of them are shared mode, so they are compatible and both of them are granted. The request of T2 is like X exclusive mode, and exclusive mode is not compatible with the other mode. Okay, so T2 cannot be granted because at the moment and already T1 and T8 has like S on item 23. So like manager cannot grant T2. T2 can be granted after releasing the locks by T1 and T8. After when T1 and T8 releases their locks, then T2 can the request of T2 can be granted, and lock manager can grant the request of T2 after releasing the locks by T1 and T8. So T2 should be wait until T1 and T8 release their locks. But T10 here, if suppose T10 has a lock S request, T2X, T8S, and T1S. T10, the request of T10 is compatible with the request of T1 and T8. But again, lock manager does not grant T10 because if it grants the request of T10, then T2 has a starvation. And because of T2, because T2 is waiting, lock manager does not grant the request of T10. A request of T10 can be granted and is compatible with T1 and T8. Okay, and lock manager can grant, but because of T2, it does not grant. Because of T2 and because of a starvation of T2, the request of T1 does not grant, and the request of T10, the request of T10 should be wait. If lock manager grants the request of T10, then T2 has a starvation, and because of that, lock manager does not grant request of T10.
Thank you, Doctor.
Okay. If there is any question,
Yes,
I
doctor.
can.
Yeah, yes, doctor. Please, when can I use exclusive lock and shared lock? When?
Uh, when shared logs are released, are unlocked, until we have logs, until we have a shared log on a data item by some transaction, the other transaction cannot lock that data item in exclusive mode. Then T2 should be wait until T1 and T8 release the lock. Suppose here T1, okay,
Okay.
executes unlock I23. What happens? When T1 executes like unlock operation on item 23, this request sends is sent to lock manager. Lock manager finds data item 23 here and search the linked list of transactions and find transaction T1. Then remove remove the record of transaction T1 from the list because uh, T1 unlocked the data item 23. So the record of T1 is removed from the list. And suppose also transaction T8 unlock item 23. Again, this request is sent to lock manager. Lock manager search data item and finds data item and then search the linked list below it and finds transaction 8 here, and then uh, this record is removed because T8 unlocked the item 23. After removing both of both T1 and T8 from the list, no T2 can be granted. The request of T2 can be granted, and the like X of T2 is granted. But before that, we cannot grant the request of T2 because we have two shared logs on data item. Okay.
Okay, Doctor. Thank you so much.
Okay, if there is any other question or if you need more explanation, I can do it.
Thank you, doctor.
Good.
Okay, this is the way that like manager manage the likes. It has a data structure which is called like table. Like table is exactly a hash table. If you know hash table, uh, hash table is a one-dimensional array, and each item in the array is a pointer to a linked list, and data items are maintained in this linked list. Below a data item, there is a list of transactions that has requests on data item, and like manager manage logs using this data structure. Okay. Let me continue. There is another protocol, or there is another approach which use logs for managing, for controlling concurrency. The other protocol, the other category of protocol is graph-based. Graph-based protocols. I means that like-based approach has two category. One of them was 2PL, and one of them is graph-based.
Look, please give me two.
One of the graph-based protocol is Tree protocol. Okay. So if we want to see the big picture, concurrency control. Concurrency control has two approach, like-based and timestamp. Timestamp based. Like-based, for like-based protocols, we have 2PL that we explained it before. We have another category in like-based, which is graph-based. Graph-based also has some methods. One of them is Tree protocol, and we are going to explain Tree protocol. After that, we explain timestamp based protocols. But at the moment, we have focused on like-based. We explain 2PL. Then we explain we are going to explain graph-based and Tree protocol. Tree protocol. In graph-based protocol and Tree protocol, we have a graph on data item. In Tree protocol, we have a tree on data item. So data items are in a tree. For example, data item A, data item B, data item C. So all the data items are in a tree, in Tree protocol. It is a directed tree. Each edge is directed. and the graph is tree in tree protocol. Nodes are a data item. We call this graph database graph. Database graph. In database graph, data items are nodes and vertices of graph. We have an edge from data item di to data item dj. If we have a directed edge from data item di to data item dj, this edge means that when a transaction wants to access both data items, data item di and data item dj, it first should access to data item I and then access to data item j. I means that if a transaction needs to work with both data item di and dj, the transaction should first likes di and then likes dj. This age shows the order of accessing data items. Data item di should be accessed first and data item dj should be accessed next. So ages shows the order of accessing. For example, any transaction, if wants to access A and C, it should access to A first and then to C, or first to A and then to B. This is the order of accessing the two data items. So we have a database graph whose nodes are data items, and we have an edge from data item di to data item dj. This means that any transaction which works with both data item, that transaction should first access to di then to dj. Let me write it here. If we have an age di dj, this means that a transaction which needs to access to both di and dj, it should access to di first and then access to dj. So the direction of ages show the order of accessing. Any question?
استاذ حسين عيني بس المايك مالتك ولا سحب عليك. استاذ حسين المايك مالتك.
Okay, let me continue. In Tree protocol, we have only exclusive likes. يعني X, only X likes. Okay. This protocol only use exclusive mode likes and do not use shared mode. So for reading and writing, we just use exclusive mode. We have some rules. The rules of protocol. What are the rules of protocols? The first rule is this. The first like by transaction TI maybe on any item. This means that any transaction any transaction that wants to like a data item, the first like may be on any data item. It can freely likes any data item. It can takes freely the first likes, the first like on any data item. There is no limitation for the first like. First like can be on any data item. But from the second like, from the second like or subsequently, a data item can be liked only if its parent has been liked before. Subsequently, a data item Q can be liked by TI only if the parent of Q is currently liked by TI. This means that after first like, from the second like, and the later request, a data item can be liked by a transaction TI if the transaction is currently liked the parent of that data item. Let me explain on the picture. For example, a transaction can like any data item of this tree if for the first request. The first like request can be on any data item. Okay. After that, the transaction only can like a data item if it has liked its parent. What does mean the parent? If there is an age from DI to DJ, DI is the parent of DJ. DJ is the child of DI, and DI is parent. So if a transaction can like DJ if the transaction has a like on the parent of DJ. If transaction has a like on DI. So before liking a child node, the transaction should likes the parent node. But this is the second rule. The third rule says that data item can be unlocked anytime. Data items can be unlocked freely. Data items may be unlocked at any time. There is no limitation. There is no limitation for unlocking. Any data item can be unlocked in any time. But for liking, there is a limitation. We can like a data item if we have liked its parent, and we have like on its parent. And
Could you
third,
repeat this point, Doctor, please?
the third rule says that we can freely unlock data items. There is no limitation. You can unlock any data item at any time. But for liking, there is a limitation, as the second rule says that a data item can be locked by TI only if the parent of Q is currently locked by TI. This means that the TI should first lock the parent and then the child. When we are locking a child node, we should have locks on its parent. Okay. But for unlocking, there is no limitation. You can unlock child, or you can unlock parent. There is no limitation. Let me explain on the picture. Suppose a transaction. Sorry. Suppose a transaction wants to like C. If it's the first request, it's the first like request, transaction can like C, and no problem. But if a transaction wants to unlock another data item, for example B, because this is not the first request for liking B, we should have a like on A. So we should like A first and then like B. But if we want to unlock, there is no limitation. We can unlock B or we can unlock A. There is no limitation for unlocking. And the last rule, and the rule, a data item that has been locked and unlocked by TI cannot subsequently be relocked. Cannot subsequently be relocked by TI. This rule means that if a transaction liked a data item and then later unliked that data item, then cannot relike it again. Uh, this is a kind of 2PL, okay? If you remember 2PL, when we liked some data item and when we unliked a data item, after unliking a data item, we go to shrinking phase and we cannot like anymore and we should just only unlike. So we have two phase in 2PL. In Tree protocol, rule 4 is a kind of 2PL, but only for data item separately. This means that if a transaction liked a data item and unliked it, then it cannot again reliked that data item. Okay, so for a data item, there is something like 2PL. If we liked data item and unlike that data item, then we cannot again like that data item. But transaction can like another data item. So in total, in total, we do not have 2PL. Just for one data item, it's like 2PL for one data item. I can explain more it by some examples. So, for example, suppose we have a transaction TI. It, for example, like X. A. Okay. The first like request can be on any data item and there is no limitation. Then if it wants to like another data item, for example, like X, if TI wants to like, for example, let me see the picture of the database graph. For example, suppose we have this database graph. A, B, and D. Suppose transaction I likes A and then wants to likes D. If transaction TI wants to likes D, it should have likes on B. The parent of D is B. It should have like on B. So before liking D, it needs to like B, then like D. So if transaction TI needs to like D, sorry, first should like B and then like D, because the parent of D is B. We should have like on B and then like D. Okay. After that, this transaction can unlike D or can unlike B. There is no limitation for unliking. Okay. Suppose it unlikes, for example, B. Okay. When transaction TI unlike B, then it cannot like B again. Okay, it is not permitted because of rule 4. Rule 4 says that when a transaction unlike a data item, it cannot like it again. So it is not permitted. But it can like, for example, an other data item, for example, C. Okay, it's okay, no problem, but it is not okay. So as you see, TI is not 2PL because here TI unlike and here TI likes. In 2PL it is not permitted. It is not 2PL.
يا سبحان الله.
It means that in Tree protocol, transaction may not obey the rule of 2PL. As you see, it is not 2PL, but TI obeys the rule of Tree protocol. But if we consider only one data item, for any data item, it acts in 2PL mode. For example, we like B here, we unlike B here, then we cannot like B again. So on B, on only one data item, it likes 2PL. Like, unlike, then it cannot like again B. But in total, for any data item, if you consider all data item, it is not 2PL because it like B here, it unlike B here, and then it can like C here. After unlocking, it again like another data item. It is not 2PL. Okay, so let me review the protocol in brief. We are explaining Tree protocol. Tree protocol is a graph-based protocol and also like-based. We have like-based protocol. Under like-based protocol, we have graph-based protocol. One of the graph-based protocol is Tree protocol. In graph-based protocol, we have a graph which is called database graph. Database graph is a graph whose nodes are data item, and if there is an age between one data item to another data item, this means that the order of accessing, if a transaction wants to access both data item di and dj, it first access to di and then access to dj. I means that it should like di first and then dj. We should like parent first and then the child. In Tree protocol, database graph is a tree. This is a tree. Okay, this database graph, a database graph in Tree protocol is a tree. Tree is a graph which does not contain cycles. Okay, as you see, there is no cycle in this graph. So tree is a special kind of graphs. So we have a database graph or a tree on data item. Then we have 4 rules. Tree protocol has 4 rules. In Tree protocol, we only use exclusive locks. We do not have shared locks. We have just exclusive locks. All the locks in Tree protocol are exclusive. And we have 4 rules. The first rule says that the first lock of a transaction can be made on any data item. So there is no limitation for the first lock. The first lock, any transaction can lock any data item if in the first request, or the first operation, the first lock operation can be on any data item. There is no limitation. So for the first lock of any transaction, there is no limitation. This means that here, when TI wants to wants to like a data item in the first once when TI likes for the first time a data item, that data item may be any data item. So let me explain on the picture. If a transaction for the first if the first request of a transaction is liking, for example, data item F, it can likes F without liking B, because the first request can be on any data item. For the first request, we do not need to like its parent, but for the second request and so on, we can like a data item only if we have like on its parent. This is the meaning of the first rule. The second rule says that a data item can be locked by a transaction only if we have lock on its parent. The third rule says that data item can be unlocked at any time. There is no limitation for unlocking. And the fourth rule says that if a data item is unlocked, then it cannot be relocked. Cannot be relocked. As you see here, if we unlock B, then we cannot lock B again. Okay, any question?
Doctor, sorry.
Please.
So for the rule number 1, I can lock, maybe I can lock the node B first, not lock the node A.
Yes.
Thank you, Doctor.
Let me give some examples here. Suppose we have transaction 10. Transaction 10, the first lock of transaction 10 is like X, B. Then like X, E. Then like X, D. And after that, unlike B and
اشتغل يلا الحمد لله ماشي انت امرنا خليك الله يبارك فيك.
unlike E and like G, then unlike D, then unlike G. Let's check it on the picture of database graph. We have transaction T10. Okay, here T10. T10 first wants to like B. Okay, because this is the first request, there is no problem. T10 comes and likes B. This is the first request of T10, so it is granted, and B is liked by T10. Then the next request of T10 is like XE. Here, E. E. This request is the second request. So if we want to like E, we should have like on its parent. The parent is B, and T10 has a like on B, so it can like E. Transaction 10 can like E because it has already like on B, so it's okay. The next request of T10 is locking D. Again, T10 can like D because it has already lock on its parent, which is B. So T10 can like D. As you see, the first request of T10 was locking of B, and it can be done without locking its parent. T10 has not does not have lock on A because locking B is the first request of T10. So for the first request, there is no need for locking the parent, and B can be locked by T10. After that, for the next request, we only can lock a node if we have a lock on its parent. So E can be locked because T10 has lock on B. B can be locked because T10 has lock on B. The next operation is unlocking B. T10 wants to unlock B. It's okay because unlocking, there is no limitation for unlocking. It can unlock B. We may think that because we have lock on D and E, we cannot unlock B, but it is not correct. Unlocking has no limitation, so we can unlock B even we have lock on E and D. There is no problem, so we can unlock B freely. We can freely unlock any node. T10 unlock B, and there is no problem. Then T10 unlock E, it can unlock E. There is no limitation. Then the next request is locking G. T10 wants to lock G. It can lock G because it has locks. It has lock on D, which is parent of G. So G is locked by T10, and there is no problem. After that, the next operation is unlocking D. Unlocking D, it is okay. T10 can freely unlock D. And the last request and last operation of T10 is unlocking G. And G is unlocked. Okay.
Excuse me, doctor. If I have another order like lock A.
Please repeat again.
If another request.
Okay.
Look A.
Okay. By another transaction or by
In this transaction. This is
transaction.
Yes.
Okay. If this transaction wants to lock A, okay, it cannot lock A because according to this protocol, any locks should be in the order of the edges. The locks should be from top to bottom. Okay, you cannot lock C and then lock A. This is in a reverse order. It is not permitted. If you want to lock C and also want to lock A, you should get the lock of A first and then the lock of C. You cannot lock C first and then lock A. It is in a reverse order. It is not permitted. Okay. So
okay,
if T10 likes B, it cannot in the following like A, because the locking should be in the direction of the edges, from top to bottom, from parent to child. Okay. Let me give some other examples of transactions and
خلاص الوقت.
review them on the picture. Sorry. What happened? Okay. T11 like XD. The first like can be on any date item. There is no problem. We can like D. And like XH. H can be liked because the parent of H is D, which is liked. So H can be liked. Then unlike D is okay because unlocking, there is no limitation for unlocking. Again, unlike H, it's okay. T12 like XB, the first like is okay, can be on any data item. Like XE is okay because the parent of E is B. B is liked, so we can like E. Unlike E is okay, we can unlike any data item at any time. And unlike B, T like X, D, the first like can be on any data item, it's okay. Like X, H, it's okay. Unlike D, unlike H. T13 is the same as T11. These two transactions have the same liking pattern. Okay, these are some examples which are legal on Tree protocol, which obey the rules of Tree protocol, and they are okay under Tree protocol. Okay. As you see, a transaction which is legal under Tree protocol may not be legal under 2PL, as you see here. In, for example, T10 here, unlike B, unlike E, and then like G. It is legal under Tree protocol, but it is not legal under 2PL because in 2PL, when you unlike a data item, you cannot like in the following a data item. So T10 is not legal under 2PL, but it is legal under Tree protocol. Both 2PL and Tree protocol ensure conflict serializability. I mean that if we obey the rule of 2PL, or if we obey the rule of Tree protocol, the schedules are conflict serializable. Okay, both 2PL and Tree protocol ensure conflict serializability. But as I said, there may be some schedules that obey the rule of 2PL, but not the rule of 3 protocol.
Okay.
Or
وين بيتهم ذولا؟
or maybe some schedules that are legal under 3 protocol but are not legal under 2PL, and vice versa. Maybe some schedules that obey the rule of 2PL but not the rule of 3 protocol. Also, there is an intersection between these two sets. Also, there are some schedules that are legal under both 2PL and 3 protocol. So we can have some examples of schedules that are both legal on under 2PL and under 3 protocol. And also there are some examples that are legal under 2PL but not under 3 protocol, and vice versa. There are some schedules that are legal under 3 protocol and are not legal under 2PL. Okay. Three protocol. In 3 protocol, we do not have deadlock. Deadlock cannot occur. Deadlock cannot occur in 3 protocol because we have we have an order on locking. We have the order of locking is according to the database graph. As you see, the locks are given from top to bottom. But it is not true for 2PL. In 2PL,
ماكو واحد من رمزك واحد من
maybe a transaction like A and then like B, and other transaction like B and then like A. It is okay in 2PL, but in 3 protocol, if two transactions wants to like A and B, both of them should like A first and then like B. And this rule avoids a deadlock. Let me give an example for deadlock. How deadlock can occur. For example, suppose you have TI and TJ. TI like XA, TJ like XB. Then TI like XB, and it is not granted and wait. And TJ like XA, and it is not granted and wait, and the deadlock occurs. This may occur under 2PL. Okay, TI like A, TJ like B, and TI wants to like B. It cannot like and wait, and it is weighted. Then like J and TJ wants to like A, and it is not permitted, and it is weighted, and the deadlock is and a deadlock occurs. This may occur under 2PL, but in tree it does not occur because if because we have a database graph, and if A is the parent of B, Ti and Tj both of them should give their likes in this order. Both of them should like A first and then B. Here Ti obeys the rule. First likes A and then B. But Tj does not obey the rule because it wants to like B first and then like A. So Tj is not does not obey the rule of tree protocol. Is not legal under tree protocol. Tj does not obey the rule of tree protocol. So in tree protocol, deadlock does not occur. This is a good point. This is a good point for tree protocol. Okay, the session is finished. If there is any question, let me know. For the next session, we are talking about timestamp-based protocols. There are some good points for 2PL, and there are some good points for tree protocol, and some bad points for both of them. A good point for tree protocol is it does not have a deadlock, but the bad points of tree protocol is that we need to like data item that we do not need liking them. As I said before, let me show on the picture. If a transaction wants to like, for example, B, it should also like, if a transaction wants to like D, it also should like B, because the protocol forces that we like we have a lock on the parent of a data item. Transaction may not need locking a data item, but the protocol forces the transaction that if wants to have a lock on a data item, also should have a lock on its parent. So in tree protocol, we should like some data item that we do not need. And this is the bad points of tree protocol. But the good point of tree protocol is that deadlock cannot occur. Okay. If there is any question, please let me know. The session is finished here. The time is over. Do you hear me?
Yes, Doctor.
Thank you very much.
Yes, doctor. Thank you.
Yes, doctor. Yes.
Okay, thank you.
Thank you.
Okay, doctor.
If there is
Thank
any question,
Okay, doctor. Thank you.
I can answer. But if you want to, in the next session, we can again explain any note that need to explain more. We have
Okay, thank you.
next session on Saturday. Okay.
Okay.
Thank you, doctor.
Thank you.
Okay.
Thank
Have
you
a
very
nice
much,
day.
Victor.